3.4 optimization problems in economics and science. So optimization problems usually arise in economics and science. In the business world, it is most profitable to minimize the costs in order to maximize profit. Okay, so that's the trade-off, and that's optimization. Okay, while working within the constraints of the workplace. Profit, cost, and revenue are quantities whose rates of change are measured in terms of the number of units produced or sold. Economic situations usually involve minimizing costs or maximizing profits. Okay, so example 1, this is a little bit of a review from, we touched on this in grade 10 and definitely in grade 11, and it's based on a revenue problem. So example 1, and I'm going to organize all of the numbers here while we read. So a commuter train carries 2,000 passengers. Okay, so what you want to start to think about is you want to think about revenue. So we'll do let R represent revenue. Okay, and then we're going to talk about price. So we're going to talk about price, which is, oh, that's fine, and quantity, which is the demand function. Okay, so when we're thinking about revenue, we're thinking revenue equals price times quantity. So in regards to quantity, originally we'll have 2,000 passengers. Okay, so a commuter train carries 2,000 passengers daily from a suburb into a large city. The cost, so immediately I'm like, okay, now this is talking about price. The cost to ride the train is $7 per person. So this is $7. Research shows that for each 10-cent increase, so we would increase this by 10 cents, 40 fewer people will ride the train. Okay, so for a 10-cent increase, we're going to have, okay, I'm going to turn this into an arrow because we're going to have another arrow, negative 40 passengers. Okay, but then for every 10-cent decrease, so if it's negative 0.10, I'm going to turn this also into an arrow. Okay, then we're going to add 40 passengers. So those go hand in hand. Okay, 40 more people will ride the train. If the capacity of the train is 2,600 passengers, so what this is going to tell us is the domain. We're going to say max, so this is the restriction. The number of passengers, so let's go quantity, is going to be between 0 and 2,600. Okay, and carrying fewer than 1,600 passengers means costs exceed revenue. So actually, let's change this to 1,600. So the number of passengers has to be between 1,600 and 2,600, and it can include these numbers because this is saying carrying fewer. That's strictly fewer than 1,600 passengers. Okay, what fare should the railway charge to get the largest possible revenue? All right, so this is what we want to do. We want to first write an equation for revenue. Okay, so what this is going to be is it's going to be revenue equals price, and all of the numbers having to do with price is going to be in one bracket, and then times quantity. And that's going to be another bracket. So the revenue is, so the price is going to be $7, and then we're going to add 10 cents. But if we leave it like this, what's going to happen is that's just going to be $7.10. So we need to introduce a variable. So we're going to introduce the variable x, and we're going to say right here, let x represent the number of increases. Let's go price increases. Okay, so if they increase the price 5 times, that'll be 50 cents. The price will be $7.50. If they increase it 12 times, it'll be $1.20. So it'll be $8.20. Okay, so we don't know how many price increases there are, so we label it X. Now quantity, 2,000 passengers, so that's what we start with. And then minus 40X. So every single time there's that price increase, we're doing negative 40. So again, if there are 3 price increases, it'd be less 120 passengers. Okay, just as an example. Okay, and now what we want to do is we want to expand this. So we can go ahead and FOIL this equation, and we get 14,000 minus 280x plus 200x minus 4x squared. Okay, I don't like when this formula is not in standard form, so I'm going to collect like terms, and I'm going to move the negative 4x squared to the front, and then a negative 280x plus 200x, I get negative 80x, and then plus 14,000. So this right here is the formula for the revenue of the commuter train. Now that we have the revenue equation, what we can do is we can solve for the derivative of the revenue equation, and then we're going to be able to find the critical points to solve for our max and min. So bring the 2 down, I get negative 8x, and then negative 80x, I get negative 80. Okay, constant goes to 0. So here is our derivative function. Now what we want to do is we want to find where the tangent line is horizontal. So we want to find where the derivative equals 0. So we're going to set the derivative equal to 0, bring over the 8x, and then divide by 8. And I get x equals negative 10. Okay, so when I'm thinking negative 10, I'm thinking price decreases. So it's okay that it's a negative number, because in the question it did give us that if we increase the price, this is what happens. If we decrease the price, this is what happens. So what we want to do now is we want to convert the domain from quantity, or the number of people, to actual price increases, because we have an equation with respect to x. So we need this, instead of quantity in here, we need to write the domain that x is between 2 numbers. Okay, so what we have to do is we have to think, okay, what is the equation for the quantity? Well, it's 2,000 minus 40x. So if we're thinking 2,000 minus 40x, okay, that's the quantity, and it has to be greater than or equal to 1,600. We can just bring over the 2,000. So we get 1,600 minus 2,000, so I get negative 400. Okay, is less than or equal to negative 40x, and then we can divide out negative 40. So I get x is greater than or equal to 10. Okay, so now let's convert the 2,600. So again, the quantity is less than or equal to 2,600. So the quantity is 2,000 minus 40x again, and then less than or equal to 2,600. So let's bring the 2,000 over. We get negative 40x is less than or equal to 600. And then we can divide both sides by negative 40. And we get x is less than or equal to 15, negative 15. Okay, so our new domain with respect to x is going to be x is going to be between, okay, I made a mistake. When we divide by a negative number, we actually have to change the inequality. So this inequality changes to x is less than or equal to 10. And again, when we divide by a negative number, we have to change the inequality to the opposite side. So x is going to be between negative 15 and 10. That's our new domain. Okay, so we have three possible max or min values. Okay, so max, because we're dealing with revenue, right? So we can either have a maximum revenue at either endpoint, so negative 15, maximum revenue at 10, or we can have a maximum revenue at negative 10, which is when the tangent line equals 0. So if you were to take r at negative 15, 10, and negative 10 and sub it back into the original, we're going to get what the revenue actually is. So for negative 15, it's 14,300. For 10, it's 12,800. And for negative 10, it's 14,400. So when taking a look at this, what is the biggest number here? Well, it's 14,400. So what this means is with 10 price decreases, we're going to maximize the revenue of $14,400. So going back to the original question, it asks, what fare should the railway charge to get the largest possible revenue? Okay, so in regards to the fare, we want to take the price, which is 7 plus decimal 1x. Okay, so if we remember, price equals 7 plus 0.10x. Okay, let's sub that negative 10 into the x. Okay, and the price is going to be $6. So we can conclude, darker, therefore, the max revenue of $14,400 is achieved with a price of $6, like fair. And we could say the number of passengers. It doesn't specifically ask for it, but if we wanted to do quantity, we would sub in the negative 10. So quantity equals, going back over here, it's 2,000 minus 40x. Okay, but then sub in the negative 10, and you get 2,400. Okay. So the max revenue of 14,400 is achieved with a price of $6 and 2,400 passengers. Okay, and this $6, this is 10 price decreases. Example 2, a cylindrical chemical storage tank with a capacity of 1,000 meters cubed is going to be constructed in a warehouse that is 12 meters by 15 meters with a height of 11 meters. Okay, so what this is, so warehouse, you can kind of assume that it's like a rectangular prism, okay? Let me see this. So it's rectangular prism, but a cylindrical storage tank. So there is a storage tank in this warehouse. Okay, and what we can do is we can assume that the cylinder is going to be the same like really the same dimensions. Okay, so we're going to get back to that. So the specifications call for the base to be made of a sheet of steel that costs $100 per meter squared. Okay, so that's obviously area because it's meter squared. So let's list this, okay? So the base is $100 per meter squared. The top is to be made out of sheet steel that costs $50 per meter squared, and the walls to be made of sheet steel that costs $80 per meter squared. Okay, so walls. Okay. So A, determine whether it's possible for a tank of this capacity to fit in the warehouse. If it's possible, state the restrictions on the radius. Okay, so for A, when we talk about the rectangular prism, we're thinking 12 by 15 by 10. Okay, so we're thinking 12 by 15, and then the full length of it is 10. Now, if you think about that, let's talk about the max radius, okay? Max radius. So the maximum radius, so the diameter would be 12, because even the diameter going up and down, it can't be 15, because then it's too big for the width, okay? But the diameter would be 12, and then the cylinder would just like not go all the way to the top, and that's totally fine, okay? So the max radius is 6 meters. Okay, height, oh sorry, I put 10. The height here would be 11. So max radius is 6, max height is 11 meters. Okay, so when we think about the volume, right, because we're dealing with a capacity, and this is the restriction of 1,000 meters cubed, so max volume is going to be V equals pi r squared h. This is the volume of a cylinder. Okay, so if we think about the volume for the cylinder, the max cylinder, with the radius of 6 squared and then the height of 11, what we get is 12,043.44 meters cubed. So yes, 1,000 meters cubed is possible. Okay, and I'm just going to put for the max radius, the radius has to be between 0, but it can't equal 0, but it can equal 6. And the height has to be between 0, but it can't equal 0, and the height of 11. Because remember, if you have a 0 radius or a 0 height, then you actually don't have a cylinder. Okay, let's replace this. Okay, so this is going to be 12. This is going to be 15. And then this is going to be 11. So of course, again, 12 is going to be the maximum, because if you had the radius of 15, it wouldn't fit in the width of the warehouse. Okay. So let's work with this. So from restrictions, write a little note. So from restrictions, if we optimize the height as like h equals 11, this is what will happen, okay? So the volume we know can be 1,000, and then pi r squared h, but h is going to be the 11. So let's divide both sides by 11 pi. Okay, so we're going to get r squared equals, because the pi is going to cancel, the 11 is going to cancel, and this is approximately 28.95. So when we root both sides, we get 5.38. So if we optimize the height, the smallest possible radius that we're going to be able to use in order to achieve that 1,000 meter cubed of volume is 5.38. So our actual domain for the radius is going to be 5.38 to 6. And that's specifically to satisfy that 1,000. Up here, we can say, like, in general, any cylinder with the radius between 0 and 6 is, but including 6, is going to be able to fit into the warehouse. But down here, we can say, okay, well, for the optimization portion, if we have a height of 11, so optimizing the height, this is what we get for the radius. Okay, so B, if fitting the tank in the warehouse is possible, determine the proportions that meet the conditions and that minimize the cost of the steel for construction. And then we're going to calculate to two decimals. Okay, so if we think about minimizing the cost, what we're going to do is we're going to minimize the surface area. Okay, so that's our goal. So for B, our goal is to minimize the surface area, right? Because the more steel that you use to make the cylinder, the more expensive it's going to be. Okay, so if we're thinking about a cylinder, okay, the top, so the cost of the top is going to be $50, but then it's going to be times pi r squared, which is going to be the area, the surface area, or the area of the top, which is just a circle. Okay, if you think about the bottom, it's very, very similar. So the base is going to be $100 times the area, pi r squared. And we think about this lateral surface here, so the cost of the walls, well, it's a wall, okay? So it's going to be $80 times, and the formula for this middle part is going to be, this length here is the circumference of the circle because it's going to go around. So this is 2 pi r, and then this is the height. So this is going to be 2 pi rh. So in total, when we think about this, we think the cost of the tank altogether is going to be, well, these two are like terms. We can write them out separately. So it's going to be 50 times pi r squared plus 100 times pi r squared. I put these together because then you can see that this is actually like 150 pi r squared. Okay, and then plus, so this is 80 times 2, so I'm going to do 160 pi rh. Okay, and just be reminded, pi is a constant. So our issue with this is that we have three variables. We have the cost, so C equals, we have a variable R, we have the variable H. So what we're going to do is we're going to find an expression for H to sub that in. So an expression for H in respect to R. So if we think about the volume, here, I'm going to do this as like an aside, actually. Okay, if we think about the volume being equal to pi r squared h, and we know that the volume is 1,000, all we have to do is we have to isolate for h, and then this expression can be subbed in for h. So I get 1,000 divided by pi r squared, and that equals h. So then what we can do is we can sub this right into here. Okay, so our actual formula now is C equals 150 pi r squared plus 160 pi r, and then 1000 over pi r squared. Okay, so let's go ahead and simplify this. I get 150 pi r squared plus, so this pi and this pi go away. 160 times 1000 is going to be 160,000. And this r and this squared will go away, and that's going to be over r. Okay, and remember such that r is going to be between 5.38 and 6. Okay, let's bring this up. So now what we're going to do is we are going to find the derivative. So c prime equals, so if we bring down the 2, we get 300 pi r, and then 160,000 over r. What we're going to get for that is negative 160,000 over r squared. Okay, so when does this equal 0? So 0 equals 300 pi r minus 160,000 over r squared. Okay, we want to find the critical points. So let's bring this over, and we're going to get 160,000 divided by r squared equals 300 pi r. Let's bring that r squared up. I get 160,000 equals 300 pi r cubed. Divide both sides by 300 pi. And what I get is r cubed equals 169.85, which gives us an r value when we cube root it of 5.54 meters. So now what we want to do is we want to find which one is the minimum cost. So we're going to find the cost at 5.38, which is one of our endpoints. We're going to find the cost at 6, which is another one of our endpoints, and we're going to find the cost at 5.54, okay, which is the potential max or min. So at 5.38, we get the cost of 43,380. The cost of 6, we get 43,631. And the cost of 5.54, when we calculate it, we get 43,344. So looking at all these options, this is the minimal cost, which is what any company wants. They want to reduce costs so that their profit and their revenue and what they take in is higher. So we can say there's going to be a minimum cost of $43,344 with a tank of radius 5.54 meters and height of, okay, solving for this height, 1,000 divided by pi 5.54 squared, and we get 10.37 meters.